Okay, well, welcome to Mo's thesis defense. This is really, I think, an exciting moment after a journey of really great educational and research achievements. So Mo came to us from University of California, San Diego, and was an exceptional student there, or I should say from his original background in Saudi Arabia. And when he came to MIT, I would say he had the most remarkable first year that I've personally witnessed. So besides doing very well in all the coursework, he joined my lab at the end of the first semester. And by the end of the next semester, he had already publication 2 papers based on original experimental work, which normally takes quite a bit of startup time. So he went right into my lab and just immediately mastered these novel methods of ion separations that we'll be hearing about today using so-called shock electrodialysis, and wrote some really excellent papers that already by even his first year substantially advanced a field of research that I've been working on with my group for about 10 years now. And so we'll be hearing about some of that. And he continued with tremendous momentum in his thesis, but then unfortunately as an experimentalist was affected quite seriously by the COVID pandemic shutdowns of our laboratories, but that didn't deter Mo. So I tried to suggest a few other things for him to work on. He contributed to some theoretical papers with others in our group, but also primarily took over a review article that I'd begun working on with some previous students already as early as 2014. So it's kind of a long time in the making. It's a review of electrochemical methods of ion separations and water purification. And Mo really turned this work into, I would say, really a magnum opus or masterpiece. It's an enormous review that covers all aspects of the field. It has almost 1,500 references. It's truly comprehensive. And so it's the first review to cover shock electrodialysis-based separations that we personally worked on with Mo in his thesis, but also broadly covers many other areas. And then when he got back into the lab over the last year, he was able to continue advancing the shock electrodialysis work into a family of methods, which he'll tell us about, that he calls shock ion extraction, where he's essentially electrified ion exchange processes using ion exchange resins with these deionization shock waves to perform separations, specifically of metals and other trace contaminants in water. But on the other hand, as he began through this review process, thinking about a wide range of different technologies, he's also had his mind on other kinds of separations that he could study, not only in his thesis, but even afterwards. And throughout his whole time at MIT, I've been discussing with Mo the possibility of founding a company together and really building attempting to commercialize some of the methods that we have been developing here. And Mo really educated himself quite independently even on entrepreneurship at MIT and took full advantage of various resources here. And he just recently won the prestigious Activate Fellowship to support him as an entrepreneur when he graduates. And I'm happy to say that we just recently founded and incorporated a company called Lithios, which will be focusing on ion extraction. And this is a topic which was not directly studied in his thesis, but really stems from this broader class of methods that he mastered and learned about throughout the writing this enormous review paper. So that's, I guess, just a brief introduction to the research. We'll be hearing more about Mo's advances on selective ion separations in a moment. I'd just like to also add that Mo's really an incredible person to work with. I consider him a great friend and co-author and fellow scientist, and it's really been a pleasure to work with him. He also works really well with others in our group, and I think has the leadership skills that will help him succeed also in business and industry as he moves forward. So I guess on that note, I'll let Mo take it away and tell us about selective ion separations by shock electrodialysis.
Hey, Martin, thank you so much for that kind introduction. Actually, I want to start by saying that one of my friends told me one time after my 4th year talk that you do give very kind and thoughtful introductions, and I do want to echo that sentiment and say how much I appreciate having sort of the ability to work in your group and being surrounded by a great cohort of smart scientists and engineers. Ladies and gentlemen of the audience, it's also my pleasure to be here and to present to you my work on selective ion separations using shock electrodialysis. Just want to make sure I get the recording right here, so I'll put myself real quick. Okay. And then we are ready to go. Sorry, it's a number of steps here to get things right, but we should be good to go. Get this out of the way too. Awesome. So my thesis is focused on selective ion separations using shock electrodialysis. And I understand to a lot of the perhaps non-technical members of the audience that this title might not immediately make sense, but my goal throughout this presentation is to parse through the different components of this title to help transmit the excitement I feel toward this research area and the importance of ion separations in modern industry. It turns out that separation techniques is as familiar as walking or eating, broadly speaking. I'll start with a rather trivial example, so bear with me. Just curious to poll the members of the audience real fast. Does anybody enjoy Skittles candy? Awesome. Most people do. I'm assuming the folks on Zoom as well. Okay, very good. And perhaps people have a preferred Skittles color or maybe even a least preferred color. I know that when I was a kid, I actually enjoyed the yellow and the red colored candies. And apparently there was this limited edition version with blue colored Skittles or whatever. The point here is actually that somehow people pulled this or studied the statistics. It turns out that yellow is the least favorite Skittles color in America. Now, why this is the case is actually completely irrelevant. What matters here is that the consumer of these Skittles candy will typically go through this mixture where sort of the different components are distinguished by their color and handpick through to pick out their preferred or leave behind their least preferred colored candy. And this is known as the handpicking method, very primitive separation technique. Now, if I were to make the task a bit more challenging, I may ask you, how would you go about separating more complex mixtures here, including larger solids from smaller ones, or even solids from liquids, to prepare, for example, your favorite tomato puree in the kitchen? And the way you would go about doing this is actually it's given away in the photograph. You would use a strainer or a sieve, and this is perhaps a common household or kitchen appliance that you would use for this separation technique. Now, if we were to make the task rather a bit more challenging, I may ask, how would you go about recovering the fresh water present in seawater and separating it from the contaminants such as organics and other salts that render this substance not readily potable? And most people would think of seawater desalination techniques broadly, which include distillation, but more so reverse osmosis as the state-of-the-art approach today in the industry. And now here's a task which I think is probably one of the more difficult ones. And this substance right here is known as firefighting foam, which contains the active ingredient known as PFAS, a family of fluorinated organic compounds that are carcinogenic and have health advisory limits as a result set at very low concentrations, something like 10 to 100 parts per trillion. It turns out there isn't really an economical and cost-effective way today to sustainably extract and destroy these contaminants. And as a result, academics and folks in industry have been developing emerging methods, what I call emerging methods, to handle this contamination. And what you see here are a variety of different applications or outcomes that one would like to achieve. And there are many different techniques in addition to the ones that I just showed that are practiced today in industry for more advanced separations. A common base separation that you may see, for example, in suspended solids and colloidal suspensions is the settling of the solids at the bottom of their carrying liquid, which is a process driven in this case by gravity, but can be carried out in an industrial setting in what's called a clarifier. And this usually drives sedimentation of suspended solids in wastewater treatment plants. And another technique that's similar uses inertial forces in a high rate spinning centrifuge to separate solids from the supernatant. Now, typically, these two applications do involve the presence of suspended solids, and this is not directly applicable, for example, to a mixture comprising ions, which would first require the use of a precipitant to convert the aqueous ions into a suspended solid that can then be separated from the supernatant using the methods involving settling. And for more advanced separations of similarly charged ions or organic compounds that are not readily amenable into suspended solids, Advanced methods, including solvent extraction, ion exchange, and electrodialysis, are commonly used. Now, solvent extraction drives the separation by essentially transporting species into a preferred organic solvent. Ion exchange drives the separation based on the affinity of dissolved ions to the functional groups of species present on the surfaces of ion exchange resin beads. And electrodialysis drives separations based on the response of dissolved components to the an applied electric field. Usually relies on the electrokinetic response of these components. And these different applications are sometimes used individually, but oftentimes in a larger process flow diagram to drive complex separations and certain applications that I'll talk about here, starting with wastewater treatment, which is a very familiar concept. And usually this involves removal of a hazardous contaminant from a water stream to recover and reuse that water elsewhere in an industrial process or to send it to consumers. Metals mining and refining is another common area that involves separating valuable minerals from perhaps lower value base metals, as well as to refine the individual metals for downstream use in other areas of industry. Another important area that actually relies quite significantly on ion separations is beverage production, as well as related areas of food processing and even perfume manufacturing, where the goal here is usually to manage and control the properties and characteristics of the beverage or food or otherwise by essentially controlling its color, odor, alkalinity or acidity rather, by controlling essentially the amounts of components present in these mixtures. And the last example that I provide here is actually dedicated to a lot of the sort of bio-focused members of the audience, as well as all the medical doctors present, which is electrolyte and toxin management, usually carried out in living organisms by the kidneys. Kidneys are these fairly complex separation, essentially organs that in the biomedical sciences space is being reproduced in an artificial fashion. So artificial kidneys, a growing area that usually will comprise a variety of different separation methods into a miniaturized artificial organ. It's a long-term vision, but I believe in our engineers. So emerging methods will typically rely on, electrochemistry to either drive or assist the separation. A lot of the methods that I talked about up to this point usually involve just membranes, are thermal-based, or involve the use of solvents and chemicals. Electrochemistry enables a few different advantages, including the ability for transformation. So in this case, the ions, for example, will undergo certain redox reactions at active electrodes to transform the harmful contaminants, for instance, into more benign species, as well as convert these components into perhaps value-added products in certain applications. Other emerging areas in electrochemical separations are based on electrokinetics and electrosorption, which are two methods that really drive selective ion separations and have the advantage of being very selective even in the dilute limit. And in fact, electrosorption is a wide class of methods here, actually, that can enable both separation and reaction in a simultaneous process. This is a big area of research that Professor Alkhadra has even focused on in his group for water treatment as well as resource recovery. You can see in the literature the significant growth in interest academically in emerging methods for electrochemical separations. And my focus in particular has been on the electrokinetic methods, in particular shock electrodialysis, to drive selective separations. And I'll talk a bit more about this topic in the coming slides. So broadly speaking, deionization shock waves as a concept can be used to separate ions. And you may be familiar with the general idea of a shock wave in the form of essentially the transport or motion of a supersonic jet traveling faster than the speed of sound, which generates a pressure jump traveling as a wave in space and time. And a similar kind of jump can be observed in the concentration profile of an electrolyte when subjected to an applied electric field in the correct type of system. And this electric field will essentially enrich ions in this electrolyte on one side of the channel, as well as deplete the ions on the other side of that channel to essentially form two phases that can be separated in principle in the appropriate device. And this sharp interface is that deionization shock wave. Now, this phenomenon has been studied mathematically, and it was even studied theoretically by simulation and experimentally. And you can see in this first simulation the formation of that sharp interface, partitioning the electrolyte into an enriched phase on the left and a depleted bulk on the other side, with transport of counter ions along the oppositely charged surfaces of the channel. Similar kind of result was observed experimentally here, as you can see, with again the same formation of that sharp interface, partitioning the electrolyte into two different phases that can be collected, presumably as product streams. Now, the main physical phenomenon that enables these kinds of separations is based on overlimiting current, which requires quick revisitation of the related method of electrodialysis to better understand. Now, electrodialysis will involve a stack of ion exchange membranes with alternating polarity. So a cation exchange membrane followed by an anion exchange membrane to basically produce channels of enriched product streams on one side with adjacent depleted streams on the other. The concentration profile of such a process will look something like this, where when no current is applied, the profile will be flat, uniform in this case. And as the applied current is increased, the concentration of ions in these depleted channels will tend to zero at what's called the limiting current, which in theory would require an infinite voltage to sustain. Certain conditions enable achievement of overlimiting current, providing these regions of extended charge depletion, which enables, again, that deionization shockwave that I mentioned. And there are many different mechanisms that enable deionization shocks at overlimiting current. And I mentioned a few here of the electrokinetic effects, starting with surface conduction, which dominates in small scale microchannels. And this is what you just saw on the previous slide, with transport of counter ions along oppositely charged surfaces out of this microchannel, forming that deionization shockwave front. Electroosmosis typically will occur in larger microchannels, and essentially you'll see the formation of these electroosmotic vortices, sustaining transport of ions between the enriched phase and the opposite end of that microchannel. And if the system is even larger, you'll see these macroscopic, potentially even scale electroconvective instabilities with vortices sustaining overlimiting current and transport of ions across extended regions of charge depletion between the two electrodes. And so up to this point, the theoretical effort and experimental work has focused strictly on overlimiting current in microchannels. And a big part of the work in Martin's group prior to my joining has focused on extending the theory and experimental effort to microstructures, which are essentially these porous materials that essentially represent a network of porous microchannels. And you can see these oftentimes in materials that are readily producible in industries such as porous glass, ceramics, and ion exchange resin beads. Now, ion exchange resin beads represent an interesting class of material because of the hierarchical porous structure that enables, firstly, favorable hydrodynamics in the interstitial space here between porous beads, but also in terms of ion transport within the nanopores of the hard spheres as well. And ultimately, the objective here is, or the outcome, I suppose, is that these systems enable now the same kind of deionization shockwave over macroscopic length scales to basically provide a pathway for scale-up for industrially relevant applications. So again, you have the formation of that enriched phase on one side with that darker shade and the depleted side on the other. And in principle, you can design a device in such a way that will basically allow capture of the enriched phase on one side and depleted on the other at the outlet of a device. So from this work, Shock-ED emerged as a platform for ion separations. The basic operating principle involves feeding a mixture of dissolved ions as well as potentially neutral components, where the ions are essentially affected by the applied electric field and are driven by the electrokinetic phenomena in the process to form those two different phases as product streams. Normally in a device, a real device will contain a physical splitter placed at the outlet of this device to partition the flow into two separate streams. Over the years, Shock-ED systems have evolved quite significantly, starting with a batch button cell device, which was the first demonstration of an experimental Shock-ED system. And here, the transport of ions was driven by copper electrodeposition onto a copper cathode. And here, the idea was that this transport would drive overlimiting current, or essentially a deionization shockwave for enrichment on one side and production of purified water at the bottom. Now, a more desirable process in industry will be a continuous one. And this was the first generation of a continuous Shock-ED prototype. You can see here the basic design which involved a fairly basic structure here and use of materials. And a big part of my work was to upgrade that design in such a way that the system was more durable and resilient to operate over longer periods of time without failing. The two common failure modes in these kinds of systems will be clogging or leaking. So typically, fluid management and handling is an important area in these types of systems. And we've developed design concepts and ideas that will allow us to progressively scale up the system into larger and larger prototypes to handle increasingly greater volumes of throughput. Now, in my work, one big area that I focused on quite extensively were the kinds and classes of separations that can be carried out by shock electrodialysis methods. And the first of which is going to be based on ions and small molecules. These are the more common or familiar separations involving small ionic metals, as well as potentially small but larger molecules that are organic compounds, which could sometimes actually pose issues for membrane-based separations given their larger chemical structure that may produce or lead to clogging or fouling at ion exchange membrane surfaces. So shock ED separations actually enables enrichment of these compounds without necessarily passing them through an ion exchange membrane, enabling this so-called semi-membranous type separation. Only one of the two charges essentially needs to pass through a membrane to produce a shock wave. This kind of or class of separation actually translates quite nicely into the second category, which are based on macromolecules and particles, including larger species like these endotoxins, viruses, or even metallic nanoparticles. And again, the basic separation mechanism here is to enrich these components into the one of the two phases of this these product streams to collect them as enriched products. And again, here these types of arrangements can be designed in a serial fashion to essentially separate ions based on their electrical charge. And in fact, the charge of these larger particles can be controlled by tuning the water chemistry or properties of the barium solution. So in my thesis, the broad summary here is that I explore applications and mechanisms of ion separations by shock ED. And I started with these two applications actually in particular on seawater desalination and removal of radionuclides from processed water. At the same time, when COVID sort of hit, I picked up a few new projects, starting primarily with this major review article, which Martin discussed, and this took about 2.5 years to publish. I'm extremely proud of our amazing team of collaborators and peers who worked on this project. It was certainly one of the biggest projects, single biggest projects that I've worked on in my life. And we think it'll have a pretty big impact on the research community and the field in general. So please take a look. I think I attached it in an email too to some folks. So please take a look if you're interested. At the same time, I worked on an area of shock ion extraction, which involves the use of special materials to boost the performance of ion exchange, as well as to demonstrate new capabilities of shock ED. And in the last chapter, I focused on a new area relative to what I had previously studied, and it is based on resource recovery, partly also inspired by this review article, which taught me quite a bit about that space. And I'll talk a bit in turn about each of these projects as we go. So I'll start with the work on seawater desalination, which involves basically taking a artificial, in this case, composition of seawater where organic compounds as well as other suspended solids have not been introduced. And here the major components which are sought to be removed are these sodium ions as well as potassium, magnesium, and calcium, which are provided or present in lesser quantities. And the idea is to feed that artificial seawater composition and recover as much of it as possible as fresh water. So we operated here a shock ED process in 2 steps. And the first step, the objective was to remove a good fraction of the salt present to lower the ionic conductivity as well as the limiting current of the system. This would enable operating the second pass at much higher applied currents. And here you can see great removal pretty much of all components across the board with certain selectivity for a component like magnesium in this case. And this was quite an interesting result that we observed, and it goes back to the intrinsic multivalent selectivity that shock ED systems exhibit. And I'll talk a lot more about the selectivity aspect in a moment. One thing I do want to point out about this specific application was the high energy consumption of the process. And this has to do with the fact that electrochemical systems will generally scale quite poorly with the concentration of the solution being processed. making these kinds of applications, in particular with shock UV, much more suitable for handling dilute feeds, or when the objective is to selectively remove a trace contaminant. And so the second application that I worked on involved removing radionuclides from reactor processed water. And this work was actually sponsored by Mitsubishi Heavy Industries, which operates these large pressurized water nuclear reactors, where the radioactive fuel in the core produces steam that runs these turbine blades to produce electricity, and the condensate will naturally accumulate radioactive isotopes of cobalt and cesium. It is desirable in practice to remove these radioactive isotopes to minimize the volume of wastewater produced, as well as to protect the operators at the plant. And the idea is also ideally to leave behind as much of the boron present as possible, since it's deliberately introduced here to control the radioactive decay process in the core. So in a three-step process, we were able to remove more than 99% of the cobalt while leaving behind the majority of the boric acid in this case. And we observed pretty favorable conditions as well in terms of a high water recovery, where the water recovery here is defined as the fraction of contaminated water recovered as fresh product. It may not be obvious why this could exceed 50% if the splitter were placed midway at the outlet, but the electroosmosis in this type of system will carry fluid disproportionately in the direction of the applied electric field to get basically more than 50% fresh product that can be recirculated back into that nuclear reactor. And again, the energy consumption here was significantly lower by actually over 2 orders of magnitude compared to the application involving seawater. And again, this has to do with the much lower concentration of target contaminants being separated, where normally the ionic species here carrying the current are going to determine the limiting current in a shock ED process. So this work actually at the same time inspired another interesting application, or perhaps were carried out in parallel. And this has to do with the removal of lead from tap water. This isn't a chapter in my thesis, but it's a work that I contributed, I think, quite a bit to. And it was led by my friend and collaborator, Juan, who is also a researcher in our lab. And we looked at basically an application here that is quite relevant to communities impacted by high levels of lead in their tap water. So normally lead is advised to be present in as little as possible, given that it is sort of a toxic contaminant with really no nutritional benefits. And in particular, the advisory limit is below 10 parts per billion. So you can see this specific resident of Flint, Michigan had drinking water with over 100 parts per billion of lead present. And the toxicological effects are more severe on children, by the way. The discoloration that you see here in these water samples is actually due to the copper and iron present. Usually, if you'll have even 100 or 1,000 parts per billion of lead, you wouldn't even be able to identify its presence until you run perhaps a more advanced analytical technique. And these residents impacted by this crisis have actually relied primarily on filtration or the use of bottled drinking water to satisfy their water consumption needs. So we saw this as an interesting area and opportunity for us to test our approach to potentially address this public health crisis by modeling essentially the tap water to comprise 4.5 parts per million of sodium and about 27 parts per billion of lead, which translates on a molar basis to about 1,300 sodium to 1 lead. So clearly here, the majority component is the sodium, which we remove, as you can see here, to a moderate extent compared to the sodium, which was removed to about 99%. Again, over the experiment here spanned a number of days and was subjected to a variety of different operating conditions, in particular applied currents. And you can see that we carried out the separation at pretty low energy consumption, which translates to about 1 cent of electricity per cubic meter by shock ED. Compare that to, for example, water filtration, which costs about 2 cents per liter, about 2,000 times more. It's fair to say, however, that the shock ED process will incur additional costs from the purchase and installation of the equipment, as well as other maintenance costs. But it does also highlight at the same time the value of using an intrinsically selective approach for this kind of targeted separation. Juan did a fantastic job actually also mathematically modeling and simulating the shock ED process with the ability here to represent actually most parts of a realistic device that gave us pretty deep insight into the mechanisms of ion separations by shock ED, as well as the mechanisms of selective ion separations, in particular toward multivalent components. And her theoretical results here were able to very nicely capture and predict the experimental data that we had obtained, and provided a very nice and insightful mechanistic view of multivalent ion selectivity in this specific application. And this work prompted further examination of removing toxic metals using what I call shock ion extraction. So up to this point in our work, we've used borosilicate glass as the porous material that drives the separations, basically. And another interesting class of materials, as I mentioned earlier, is based on these ion exchange resin beads, which are normally hard porous spheres that can be bound into an immobilized wafer using a polymer binder. And we can see intrinsically that these materials have a very high ion exchange capacity and can significantly improve the selectivity toward a variety of different multivalent ions shown here. These are heavy metals relative to sodium at a variety of different operating conditions as well, including flow rate and applied current. One thing we also tested was to compare an unelectrified ion exchange process to an electrified process. And in the first set of experiments, you can see a typical ion exchange breakthrough curve where the maximum extent of ion removal is greatest initially at t equals 0. This is bed volumes as a proxy for time. You can see that the ion exchange removal essentially declines over time until the ion exchange resin beads are saturated at about 300 or so bed volumes. At this point in a real process, the ion exchange resin beads will be replenished or regenerated using strong acid, and the process is going to be repeated cyclically to continue to remove contaminants. In the electrified case, you see this region denoted by the red colored box. The extent of ion removal can be massively increased by electrifying the process compared to here the maximum extent of ion removal by ion exchange alone, which is given by this dashed black line. What you also see is, again, an increase in the intrinsic selectivity compared to a vanilla shock EV process. And again, actually not again, but rather you can see another interesting feature of these results is the decline in performance over time. And this has to do with the fact that in a mixed wafer ion exchange resin beads, hydroxides are typically formed at the junctions of opposite polarity resin beads, as well as membranes that produce insoluble metal hydroxides that could, in this case, clog the device and actually diminish the performance. There are several ways to overcome this limitation, in particular by redesigning to some extent the system, as well as by operating the system at the right conditions to regulate pH and manage the formation of these insoluble contaminants. Heavy metals in general are tough to work with using electrochemistry for this specific reason. But again, the speciation of these metals can also be leveraged for certain separations. And in particular, one area that I looked at was to essentially separate heavy metals for the purposes of resource recovery from spent catalysts. Now, these catalysts are commonly used in the chemicals and chemical engineering industries to enhance the rates of chemical reactions. And normally these catalysts will carry a variety of different critical minerals, and the idea here is to ideally recover as much of them as possible. So a typical composition may include cobalt and nickel, which you can see have the speciation designated as cations. These two components normally will form divalent cations in particular, and the other three components will normally form a family of oxyanions. So there's a clear, perhaps, way to partition these two components based on their speciation. And the idea is to accumulate the cations into the catholyte stream of a shock EV process that is recirculating, where the oxyanions will then be accumulated in the enriched product stream. So this partitioning happens right about midway down that table. The oxyanions are a lot more tough in general to work with, and this is well known, because they form these large families of metal oxyanions. You can see for the vanadium, molybdenum, and the tungsten, where these chemical equilibria essentially are controlled by the compositions of the species present, as well as by the pH. Converting this data into more meaningful diagrams using a thermodynamic simulation produces these distribution diagrams that you can see here, which essentially correspond to the vanadium, molybdenum, and tungsten. And the idea is to operate the system at the appropriate conditions to recover these components or separate them from each other. If the objective is to remove all components proportionately, then we would operate the system at the highest applied current in panel C and at near neutral pH, where all components here are removed nearly equally. If the objective, however, is to separate them from one another, then we would operate the system at a more acidic pH, which would produce or correspond to more interesting distributions of these components to achieve higher separation factors of, for example, tungsten relative to the other two components. And then this type of process can be operated in serial fashion to sequentially recover the different components and enrich them without needing to use, for example, special solvents, special materials, or specific chemistries for this kind of process, which is typically the state-of-the-art approach for metal separations in industry today. So from my work, I've demonstrated, I think quite convincingly, that ShockED is a versatile platform for a variety of different selective ion separations. And a big part of my thesis focused on understanding the device design as well as material selection for these kinds of processes to enable specific ion separations. Another part of my work looked specifically at the applications as well as capabilities of a ShockED process to enable, for example, separations of different ions, as well as some ongoing work that actually never made it to the thesis, looking at these PFAS compounds, which are of great interest today to many players in the industry, as well as to the government too. One thing I would say, I'm definitely a very application-oriented person. I like to build things that can be applied and pertain value to a customer. And actually, Martin already kind of gave away my thunder here a little bit, but I do want to mention that my sort of entrepreneurial drive has motivated me to pursue a startup. And so Martin and I recently co-founded Lithios, which is a startup focused on advanced lithium extraction. The techniques that we develop for this business are inspired, but not necessarily based directly on my thesis work. And in fact, we think that this is a very big target industry to actually be in right now, and are very excited about the prospects in the space for lithium recovery. And in fact, a lot of this work, certainly my inspiration to pursue this entrepreneurial journey, which is pretty tough, would not have been possible really without support from the Activate Fellowship, which is the 2-year entrepreneurial program that is sponsored by a nonprofit organization supporting entrepreneurs on a mission. So, I'm very excited about where we're headed with this, and please stay tuned for some more exciting results. With that, I would like to acknowledge a lot of the folks that have made this work possible, starting obviously with my family, my parents in particular, without whom I wouldn't be here and I wouldn't be the person I am today. So thank you again so much for everything that you do. At MIT in particular, I would like to deeply thank Martin Bazant, my advisor and now business partner, for the privilege and opportunity to work in his research group and to be surrounded by a great cohort of amazing scientists and engineers who have really motivated me and inspired me to be the best possible scientist that I can be. I also want to acknowledge Wanhan, who is my good friend and classmate, working on shock electrodialysis, but more on the theoretical and modeling side. And our work has been quite synergistic over the years to actually produce some meaningful results that we think are going to be pretty impactful, as well as the greater Bazant group as well. There are so many friends here to enumerate. Definitely, the best part of being a student at MIT is just being surrounded by an awesome cohort of folks. A lot of members of the audience here, a lot of people on Zoom, and people who simply couldn't make it. Thank you all for being the people you are. It's been an absolute privilege and pleasure to know you. There are some even non-human friends present in this deck. In fact, so I don't know if Brandon's here, but Brandon has another cat named Momo, whose name apparently was inspired by me. I don't know if that's the case, but that's what he says. So that's pretty cool. Additional acknowledgements to make here. I added another photo that actually includes Alan, since he was only present in spirit earlier. But these are sort of the closest friends that I made here at MIT, among many others. They've just been absolute joy and pleasure to be around and work with. And so a big part of my thesis is focused on separations, but certainly some friendships and relationships are inseparable. So it's been a privilege to know you all. I include this machine right here, which is the MIT, the department provided laptop, which has certainly carried me through the past 4 years. It's the only laptop that I've had. I know that's pretty unusual for most people. They'll have their own, given how risky it can be to rely just on this one. I will say that for me, the machine symbolizes a lot more than the laptop. Actually, it symbolizes the significance and impact of the staff at MIT, as well as the including the gym staff, the dining folks, administrative, and so forth, who really make MIT the place that it is and enable operations at the university. So thank you all. I know there's some people on the call here. Really thank your contributions. And there's one more acknowledgement here, probably the most important one of all, and that is Chipotle, which has been a major source of fuel and nutrition for me to make all this work possible, to be honest. So thank you to the folks there. Thank you to everybody in the audience. It's been an absolute pleasure to have you. Happy to take any questions. Thank you.
Well, thank you, Mo, for a very stimulating presentation. Lots of information there, and I'm sure there will be lots of questions from the audience trying to clarify. So, do you have any questions?
Thanks, man.
So you showed a lot of graphs with mixtures of many ions. Is it possible to rationally predict sort of the selectivity of different ions at the different currents or whatever?
Great question. There are certain ways to, let me go back to perhaps a more relevant slide here. I would say that prediction would normally involve, a theoretical simulation of some kind. And the ability to predict these kinds of separations is not always straightforward. It is possible, but there's complexity that arises when you have very many components, like in the example here with the toxic metals. And as you can see, it is not the most refined data set, perhaps. And again, this has to do with sort of the different affinities of these species for the surfaces of the porous material, transporting them. You know, the ion exchange resin itself will have different affinities for these different components, which can be studied and has been studied actually quite extensively in the ion exchange literature. I would say also the speciation of these compounds or components is not always fully understood, and we saw this to be the case definitely with these metal oxyanions. If you're operating at sort of near neutral conditions, standard conditions, then perhaps that wouldn't be too unobvious. But even operating slightly away from that can lead to very interesting distributions that may sort of divert the reality from what you would expect. Thanks.
I was just curious for the heavy metals. You show these plots for like days and days. Is that kind of stay apart in the field? I just don't know that much about these separations. Is there any way you can like shrink that timeline down, or is this kind of as good as you could get for separation?
So you're perhaps thinking specifically about this stuff right here?
Yeah.
So in fact, that's a great question. These are separations operated at steady state. So the idea here is that we want to show actually deliberately that this can be operated for many days, which is typically desirable for applications in water treatment or other areas of industry. Definitely, normally we have sort of short-term studies, and most of the work that you see in these slides is actually based on a few hours of operation. But here we actually wanted to demonstrate that we could maintain operation over many days without failure of the device, which is probably a common limitation of academic basic science studies, which certainly can't operate for extended periods of time. But yeah, thank you for that question. I see a hand raised in the chat.
Yeah. Hey, Mo, can you hear me?
Yes, we can hear you.
Well, firstly, congratulations on just the culmination of all this hard work. Your dedication never ceases to amaze me after now almost 10 years of knowing each other. So firstly, start there. Big round of applause. And my question is kind of on the flip side. You're selectively separating and as a result, like fouling, and I guess I could think of it as, depositing onto surfaces. Have you considered or looked at, the flip side of this as like an opportunity for selective depositions, and maybe in other spaces where where, you know, selectivity for rather than removal, but using it for building something, you know, like ALD or CVD type processes where selectivity is super critical.
That's an awesome question, Colin. Thank you for that. Also, thank you for the compliments there. I do want to go back to a slide which does talk briefly about the deposition. It wasn't part of my thesis, but there was a study on a concept called shock electrodeposition. And the idea is to basically combine the phenomenon of these deionization shock waves that you saw for selective separations, but also to form layers of these materials on a surface. And the closest thing I can show you perhaps that I have on a slide here is the mechanism by which this batch blood cell device was operated, involving copper electrodeposition on a cathode. And the idea here is that it'll drive growth of some layer, passivation layer on the cathode. In this case, perhaps building a copper cathode wasn't the objective. The objective was to produce purified water, but there are some other applications that could rely more so on the production of a different material or formation of special surfaces using this shock electrodeposition technique, which was certainly studied in Martin's group by a previous researcher, actually. Great question.
Interesting. Thank you.
Yeah, definitely. There's a pretty common industrial method known as electrodeposition. I mean, that's what it's called. It's up here lumped in that data set, but it again relies on the same effects or principles here to either remove contaminants or recover resources selectively.
First of all, congratulations, Tom.
Thanks.
It's a very thorough presentation and awesome body of work you've developed. I had a question about the stuff that you're going to do after this. So
Please.
For advanced lithium extraction, you mentioned that you were working on ideas that were kind of inspired by, but not exactly related to this particular topic. Can you maybe just say a couple sentences about like what the market needs there and why shock electrodialysis can not be the exact, you know, match in that sense?
Amazing question. Yeah. So in the space of lithium extraction, the current methods, I have a full pitch deck here. Maybe some of you have even seen parts of it, but I'm not going to pull it up now. The idea is that the current methods for lithium extraction are really, there are only two. One is based on extracting lithium from hard rock. That's a typical mining process. And then the other common one is lithium extraction from salty water known as brines. The methodology in the brines case is quite primitive, and it is very resource intensive, time consuming, and low yield method. It would be much preferred to have a method of direct extraction based on a selective component, such as a selective ion exchange resin or a selective electrode, to capture the lithium while leaving behind pretty much everything else. This would accelerate the timeline of lithium production, it would improve the process economics, the performance, and so forth. But generally, the concentrations of these brines, by definition, is going to be very high. And as we saw, for an electrochemical method that is not immediately intrinsically selective for a specific component, the energy cost will simply be prohibitive. This is why shock ED cannot perhaps directly be used for lithium capture. However, it could be tuned in a few ways that I'm thinking of, by using, for example, a lithium selective membrane, for example, actually right here, based on, for example, a ceramic solid electrolyte or a mixed matrix membrane to block the passage of most other species where lithium would be the only charge carrier in the system, basically. I think one company trying to commercialize not shock ED, but standard ED, so with this membrane arrangement minus the ion exchange resin, and they observed pretty high. I talked to their CTO actually extensively, and he told me that the energy consumptions with these kinds of methods is simply too high, that they will only be using that as a post-processing step after a first pass using ion exchange or solvent extraction for them.
Thank you also for the really fantastic talk and the
pleasure.
awesome work. I had a question related more to the also things you didn't quite talk about, but the PFAS I was curious about in terms of things that have separated those. I think those are neutral compounds, right?
Great question.
I was just curious if you could expand on like what effect electrodialysis has, that whether it's like the dipole of the carbon fluorine bond or.
So let me quickly quickly show you the application on PFAS. PFAS is an interesting set because it's just a family of a lot of different compounds, many of which, like you said, Bert, will be uncharged, some of which have end groups that are actually acidic, so that you will have perhaps an overall fairly weak charge, depending on the pKa of this stuff too, and the operating conditions and the water pH. But generally, these PFAS, these fluorinated organic compounds, are present in extremely low quantities, making a standard adsorption-based method or others quite challenging to economically remove them. So what I'm working on right now, and we'll probably have to work on for another week or so to get sufficient data, is to look at PFAS separation simply by enrichment into this top phase of that device. So I'm essentially not passing it through a membrane, which has posed problems for other ED type methods. In fact, one of our collaborators has been designing special membranes for these kinds of separations. And I think that will be a nice scientific demonstration, but difficult to scale up depending on how much nano engineering needs to be done. So the idea here is that the separation can be driven without passing the component or compound through a membrane, and it would apply, like you said, primarily to these organic, these acidic rather, PFAS compounds. So they'll have either a sulfone or a carboxyl group at the end. For the neutral components, I mean, generally speaking, you can displace neutral particles in certain electrokinetic mechanisms based on their permittivity, for example, or for even a very deep body of theory that Martin studied in his group based on induced charge electrokinetics. These small molecules perhaps wouldn't exhibit the same effects. That would probably pertain more so if you had, let's say, a neutral silica-based nanoparticle. In those cases, yes, you could have some electrokinetic displacement, but I don't think it would be big enough to make the applications worthwhile. I actually have never tested that. I have tested metallic nanoparticles, which do bear a surface charge. And for those, certainly the separation works in a similar fashion or outcome, at least, to what we've seen for the small ions.
Thank you.
Appreciate it.
Great talk.
Thanks, Kevin.
I had a quick question on, it was like a couple slides after this, we were like 13 or 14 or something. You had mentioned that species with larger charge generally have a larger driving force for separation. But I think the one of the plots we showed in potassium was more separated than calcium. And so I was curious if you could like just help me understand the results like from that plot and whether that was,
Yeah, Kevin, that's a great question. Something that puzzles me a little bit even till today, because yeah, naturally you'd expect, for example, in an ideal situation, the magnesium and calcium to be removed, perhaps in similar proportions. I think you're referring particularly to this plot right here, for instance, or even to this one here with the selectivity, where the calcium is perhaps removed to the least extent compared to everything else. My best guess as to why this occurs is due to the formation of calcium oxides or hydroxides in this process. The pH isn't too high, but normally for seawater, it's going to be slightly above neutral. So you may have some excess hydroxyl groups that do form weakly charged or even neutral calcium compounds. I did run a basic, I used some online software for thermodynamic simulation to see what are the sort of solubility limits and or coefficients for calcium hydroxide and oxide. And it doesn't seem that they do form these compounds until pretty high pH, over 10, which is certainly not where we were. And for that reason, I still am not fully certain why that may be the case, actually. But that's my best guess as to why that's for some complex water chemistry.
There are no other questions. I'd like to thank Mo once again for a great presentation and a great discussion.